x lambda is given by the net benefit function. So summation from I equal to 1 to 3 ai 1 minus exponential minus bixi minus lambda, which multiplies summation in I of the xi minus q. This is my Lagrangian. Now, what I have to do is to compute the partial derivative of Lx lambda with respect to each xi and equate it to 0. But I have an additional variable, which is lambda, and therefore I have also to compute the partial derivative of the Lagrangian x lambda with respect to lambda and equate it to 0. And therefore I get 4 equations, because the partial derivative is computed with respect to each xi, and therefore I have 3 partial derivatives with respect to the xi's, plus 1 more partial derivative with respect to lambda, so I have 4 equations for how many unknowns? For the xi's, which are 3, plus lambda. And therefore I have 4 equations in 4 unknowns. It can be solved. And the way it is solved is very simple, but I'm not solving it. Because, first of all, let me emphasize the fact that when you compute the partial derivative to lambda with respect to lambda and equate it to 0, you get again the constraint. Because the partial derivative with respect to lambda, if you look at the Lagrangian, lambda doesn't appear here, so this term disappears when you compute the partial derivatives. While here, the partial derivative with respect to lambda is given by summation of the xi's plus minus q. And therefore you get back to the equation which tells you x1 plus x2 plus x3 minus q equal to 0. So you get back to the constraint again, and therefore you have to focus on the 3 derivatives with respect to the xi's, which are easy to compute because, as I said, the function is nice. And from these partial derivatives you can compute the values of the xi's. You see that here it's easy. I'm not showing you the details, but it's very easy to express this relationship in a way that gives to you the xi's. And therefore you can substitute the values of x1, x2, x3 here and find the value of lambda. And once that you know lambda, you go back to this equation and you compute the xi's. Okay? I'm not, as I said, I'm not going into the details which are presented here. You get here the final solution. I'm not asking at the exam to carry out this exercise. I might just ask you to provide to me an example, and you can just remember what I have written here. And the remaining part is just trivial computation. I'm sure that you didn't understand how it works as a trivial computation because I didn't write on the blackboard and I didn't explain to you, but this is not really relevant. It's just a trivial computation. What I'm really interested in is that you got the conceptual meaning of this, because now I would like to move a step forward. Again, dealing with this method, I want just to mention to you how you can deal with inequality constraints. And just I'm curious, do you already know how to deal with inequality constraints in the method of Lagrange multipliers? And you told me that you... Yeah, okay, fine. And what about you? No, you didn't know this method before. Okay, so let me just move forward with inequality constraints. And in order to move forward, it's necessary for me to make sure that from a conceptual point of view, you understood how it works. So if you have any need for clarification, just let me know. Now, what is an inequality constraint? It is a constraint of the type x1 plus x2 plus x3 minus or equal than q. I am curious, what was the subject where you considered the Lagrange multipliers? In italiano, così.
Sì, per le tubazioni per trovare la portata.
Okay.
Per trovare il diametro.
Civil engineering o laurea triennale?
No, in specialistica,
Specialistica, cioè civil engineering?
No, ingegneria civile in italiano.
Ma la specialistica? Certo. Ah, perché voi sì, scusate. Sì, perfetto. Okay.
Per trovare il diametro ottimale della rete,
Okay.
praticamente.
I was just curious to know in which course they already, okay. So basically you have this kind of inequality constraint which can be written as gx minus b is less or equal than 0. And you know, this is a kind of constraint that it might happen in water resources management because not always you are forced to use all the water. Especially if using all the water doesn't lead you to the most convenient solution. The most convenient solution could be a solution where you don't use all the water. And this frequently happens when you have costs associated to the project. So like the designing of water distribution network, if you want to bring more water to people, you have to increase the diameter of pipes, and this means an increase of the costs. And at a certain point, it might be that the increase of the cost is greater than the increase of the benefit. So it's better not to use all the water. And therefore, the constraint could be of this type, which is not easy to deal with analytically. And the way in which we deal with it is to introduce an additional variable, which is a dummy variable, and gx minus b plus s square equal to 0, where s is an additional variable. Now, what does this mean? This means that the Lagrangian, and please allow me to modify the formulation that is already on the blackboard, I may wait for you to write it. The Lagrangian is, of course, modified in this way, plus s squared. But s is a variable. So first of all, just to draw your attention on the fact y squared, because you want to make it positive in any case. Because this is an inequality which is lower or equal, which means that you have to add something positive if you want to transform this inequality in an equality. Now, the problem is that we have an additional variable, so we have an additional partial derivative. And let me add the additional partial derivative here, which is partial derivative of Lagrangian x lambda s with respect to s. And let me add in any partial derivative the additional variable s. And even here, where is my Lagrange here? So what is the result of this partial derivative of the Lagrangian with respect to s? The result is minus 2 lambda s, which is equal to 0. I write it again here, minus minus 2 lambda s equal to 0 leads to two cases. Lambda equals 0, s equals 0. And this example is not reported in the slides, so please be careful. Now, we ended up to two cases. Lambda equal to 0, s equal to 0. What do they mean? Let's consider the case lambda equal to 0, and let's look at the Lagrangian. Lambda equal to 0 means no penalty. So, the first alternative, because remember that these two solutions are two alternatives. So either is through the first or is through the second. So better, either we get the maximum benefit with the first or we get the maximum benefit with the second. So the first case leads to no penalty, which means that you find the solution that you get with no penalty, just by equating to 0 the partial derivatives of the net benefit. And once that you got to the solution with no penalty, you have to look at the values of x1, x2, and x3. Check if their sum is lower than Q, and if it is, compute the net benefit. If it is not, it means that this possible solution doesn't lead you to any real solution. So this is one possibility which is not leading you to any solution, which means that the second solution would be the correct one for you. But in the case that you find a solution that is suitable, meaning that, again, x1 plus x2 plus x3 are lower than Q, then you compute the benefit and keep it in on your desk, because this is a feasible solution which leads you to a benefit. And then you keep it on the desk, and we go to look for the second alternative. Second alternative, s equal to 0, which means equality constraint. So, in this case, let's find the solution given by the equality constraint, and let's compute the benefit and keep it on our desk. At this stage, we have possibly two competitive solutions, or just one if the first one didn't lead you to any suitable solution. If you have two solutions, then you just have to look at the solution that gives to you the highest benefit. And this is the final solution of your problem. Please consider that by including an inequality constraint, you ended up with a more complicated problem with two alternative solutions that you have to check. So, any constraint, this is like a conclusion, a concluding remark. Any constraint to your problem leads you to an additional variable. Because let's suppose that you had two constraints, not just one, then you have to add two penalties and two different multipliers, lambda 1 and lambda 2. So any constraint adds an additional variable to the problem. So think that besides the decision variables, you have additional variables as many as the number of constraints, equality constraints. Any inequality constraint brings two additional variables. So you can easily understand that this analytical solution can become easily unmanageable if you include many constraints, and especially if they are inequality constraints. Okay. With Lagrange multipliers, I'm done. And what I may ask at the exam is just what I mentioned by voice. I will not go further. Now, what if I have to consider multiple criteria? Not just the economic criteria, but multiple criteria. Like, let me make a very simple example. Let's suppose that you have to get water from the river. You are asked to design water withdrawal from a river. And then you have, of course, you have to decide how much water to get from the river. And you have some constraints, like the release of the environmental flow, which is prescribed by law. So you have some upper limits to the amount of water that you can take, once that you quantified the water that is available in the river. And of course, the more water that you take, and the more benefit, gross benefit that you take from it. And then you have some costs. So one criteria is, for sure, in water withdrawal, the economical benefit, the net benefit. But there might be other criteria, like minimizing the environmental impact, or keep the environmental impact in terms of downstream ecological condition of the river. So we might be asked also to consider this criteria, because the more water that we take, we increase the benefit, but also we decrease the ecological status of the downstream river. And you know, at the beginning, when you start getting water, you get a lot of benefit, and the environmental impact downstream is still not really significant, because if you have a lot of water and you take just a minimum amount of it, downstream you don't see almost any impact. And in the meantime, you get a lot of benefit, because usually, as you have seen, the benefit function increases very rapidly. But as long as you keep trying alternatives which consists in deriving more water, you have the benefit that it is increasing slower, and then you have the environmental impact downstream that is increasing faster. So people may ask you to find the best compromise between environmental impact and the net benefit. So you have two very different criteria, and the environmental impact is difficult to quantify in terms of money, so it's difficult to quantify it as a cost. And you get two criteria to consider. And basically, you have two big problems here. And the first big problem is to associate a numerical value to the environmental impact. If you want to write an algorithm, if you want to consider the environmental impact through an analytical procedure or a numerical procedure, in any case, you need to associate the environmental impact to a number. Otherwise, if you don't associate it with a number, of course you could, you could decide based on your feeling, like, yes, this environmental impact is too much, but it's difficult to reach an agreement between people. If you don't find a number which is agreed by all the stakeholders to quantify the environmental impact, the discussion becomes unmanageable. So if you want to get a manageable discussion, you have this first problem. Let's identify a number, an indicator, an index of environmental impact. Otherwise, and then you have two numeric criteria, which are very different, because on one hand you have a cost, on the other hand you have a number, which not necessarily is a cost and probably is not. And therefore you have two criteria on which you have to take your decision, and they must be combined. And combining them means, let me say first of all that one possible option is to combine them, and combine them, which is not the only one option. Then I will explain you later that you may have other options, which consist in keeping the criteria distinguished. But the most obvious option is to try to combine them. And if you want to combine two numbers which have different measure units, you have two operations that you have to perform. First is rescale them in order that their range of variability is the same. So like bring these two numbers in the range 0, 1. This is what is usually done. And then you can combine them, but when you combine, you need to introduce a weight for each number, meaning what is the importance of the net benefit with respect to the environmental impact. So let's suppose that I can define the net benefit between 0 and 1, where 0 means no satisfaction at all by the person that takes the benefit, and 1 means maximum happiness. And let's define the environmental impact with a number that is varying from 0, 1, where 0 means no impact at all, and 1 means the worst impact that you can think of. Okay? Then you may find a design, a solution, a decision that brings you to a benefit of 0.5 and an impact of 0.3. So if you want to combine these two numbers to get to a unique number to maximize, you need to introduce a weight, which quantifies the importance of the economical benefit with respect to the environmental impact. So if you ask to the person that is investing the money, he will say, to me the weight is all on the economical benefit. If you ask to the fishers downstream, they will say, to me the weight is all on the environmental impact. So if you find a way to rescale these numbers and combine them in only one number, then you get a function that you can optimize. So this is one possible solution. One possible solution, again, is to combine the criteria and find the optimum. And again, this leads you to two major problems: rescaling and weights. Good. Other possible solutions are to keep the criteria separated. I'm not sure we will have time to deal with these criteria. There are methods for keeping them separated. And let me say that if we have time, I will show you some examples. But for now, I am introducing the method of combining the criteria through rescaling and weight computation. And I'm starting from this method because it's by far the most traditional and the most used today. First of all, let me deal before I stop with the problem of rescaling. So basically, what you have is a decision variable, which in the example that I make is water withdrawal. Amount of water withdrawal. You can indicate this decision variable as Q, where Q is the river flow that you take from the river. And of course you may have some constraints, like that you have to make sure that downstream the environmental flow, which in Italian is called with the symbol with the acronym DMV, which stands for the flusso minimo vitale, in English it's called environmental flow. Let's say that the environmental flow must be equal to an assigned value, an asterisk, whatever it is. Which means that when you design your water withdrawal, you have to make sure that by taking an amount of water equal to Q, you respect this constraint. And usually keep into account that when you design such a water withdrawal, Q is your maximum amount of flow to be taken from the river. And it's the design flow for instance, for your pipes that bring the water downstream, or for your pump to take the water from the river. It's a design flow, and it may happen that you don't take the full Q flow, because you look at the river, you make sure that downstream you have the environmental flow, and then you may end up with a withdrawal which is less than Q. So usually Q is the maximum. You design the maximum amount of water that you can take. Okay? And now, your first task is to compute the net benefit, which is a function of Q. And usually, you can draw it in a graph, and therefore you have your net benefit, which is a function of Q, depending on Q, and it can be a function like this, which may converge to a maximum or may not converge to a maximum, but usually it increases faster and then it increases slower. And then you have the problem that depending on Q, you also have an impact downstream, and you have to define some curve which quantifies the impact. And let me say that a way of computing this rescaling is through the use of utility functions. Do you know what is a utility function? And basically, let me define a utility function in a way by referring to the net benefit. And the utility function is defined in this way. Let me define the utility function of a net benefit Q and let's say that the utility of the maximum benefit, I am already providing a definition. The utility of the maximum benefit is equal to 1. The utility of the minimum benefit is equal, of course, to 0. The minimum benefit usually is 0, but you could put a lower limit, like I may say, if the benefit is lower than this amount, for me, is like I didn't have any benefit. So I could put also the utility of this benefit. I could put the minimum here. Because an investor could say, if you don't give me at least this benefit, I don't invest the money. So then you give 0 this benefit. And you have a condition to satisfy. the derivative of the utility with respect to the benefit should be so the utility must be a non-decreasing function of the benefit. So basically, you have a function, utility, depending on the benefit, and you have the benefit here, 0, 1. This function can be, for instance, like so. And be careful, if you do like so, this is NB max, and this is NB min. What does this function do? Just rescale in the interval 0, 1 the range of the feasible benefits. Now, in the same way, first of all, let me anticipate, I'm closing, that this function, I drew a linear function here, and could be non-linear, it could be like this, or could be like this, as you want. The only condition that you have to satisfy is that the minimum is 0, the maximum is 1, and it's a not decreasing function of the benefit. And be careful, if you use this kind of function that is has the concavity upwards, it means that you are giving a very low utility to benefits that are far from the maximum. So this is a kind of investor that really wants to get a lot of money. The opposite instead is a kind of investor who is happy even if he gets less money. So they are very different. This utility function depends on the investor and the people whom you ask, and they are very different. And let me now close by saying that the same thing can be done by defining a utility function of the environmental impact with respect to Q. And usually, what you obtain is a variation between 0 and 1, and you start from you start from 1 if you don't take any water, in this case. And therefore, of course, the definition is to be adapted. Okay? So you start from 1 if you don't take any water, and then you may say that you give an utility of 0 if you reach to an amount of water that, accordingly to your perception, is really causing the destruction of the environment downstream. And therefore, you may have a linear variation or different kind of variation. Of course, the lower curve is a prudent curve. You converge rapidly to 0 utility for increasing water withdrawal, which means I am really prudent. I have the maximum of utility for no withdrawal, and as soon as I start getting water from the river, my utility goes down, which means I'm very prudent. On the other hand, if I stay in the upper part, then I am less prudent because I keep a lot of utility even for increasing withdrawals. So you see that now you have two different values of utility, one which increases with Q, which is related to the benefit, and one which decreases with Q, which is related to the environmental impact. And therefore you can combine the two and find the maximum of the utility. But of course, to combine you need the weights. will see next week how to move forward. Tomorrow, sorry, I forgot to tell you one thing. This is, I can give you the printout, just you are three. So, Professor Bolizetti told me to tell you to download this software, which is given at this address here. And I hope that you can copy now the address and use just one printout, because I wanted to print on the blackboard. But okay, you can just take a picture, thank you. And you of course you have to take the appropriate version, 32 or 64 bits, and then install it on your PC. And he told me that if you get in trouble in installing, he will explain you tomorrow how to install it, but he wanted to give to you the preliminary advice so you get the file and you are ready to install. And if you are not successful, he will explain to you how to do that. And as I mentioned to you, for the part that was done by Professor Bolizetti, and everything is fine. On next Monday, I want to discuss with you how was the experience, because I want to get your feedback. And also we can take an agreement on the questions that I may ask at the exam. Maybe not really next Monday. Next Monday we start discussing it. And then for the questions, you just explain to me how was your feeling, and if you feel comfortable with some parts of the program, and above all, if you don't feel comfortable with part of what he said. And therefore we can take an agreement, okay?